This project cost billions of dollars, took years to build, and some experts believed it should never have worked. But somehow, it did. Welcome to Next Gen Engineering. Today, we're breaking down the insane engineering behind this project. Step by STE. The insane engineering of the F-35B. The physics of vertical flight, stealth, and compromise. Opening the impossible equation. In 1986, a British test pilot hovered 50 feet above the runway in a Harrier. The aircraft drifted just slightly. He corrected. The engine spooled. The jet wobbled again. And then gravity won. Vertical flight in a jet fighter is not just difficult. On paper, it shouldn't work at all. Because the equation governing hover is brutally simple. Thrust greater than or equal to weight thrust / Jack weight thrust greater than or equal to weight. If thrust drops even 1% below weight, the aircraft falls. No glide slope, no forward velocity to generate lift, no aerodynamic cushion, just raw thrust versus gravity. For 50 years, engineers have tried to cheat that equation. The British built the Harrier brilliant, dangerous, and maintenance-heavy. The Soviets tried and largely failed with the Yak-38. The Americans studied vertical flight and mostly walked away. Because the physics is cruel. And then came the requirement that would break aerospace engineering. The United States Marine Corps wanted a stealth fighter. It had to fly supersonic. It had to carry precision weapons internally. And it had to take off vertically from short amphibious assault ships. In other words, it had to hover. It had to be invisible to radar. And it had to perform like a modern fighter. Those requirements are mutually hostile. And yet, the result is the Lockheed Martin F-35B Lightning II, arguably the most mechanically complex fighter ever built. This is the engineering story of how it works, and why it almost couldn't. Part 1, the context. Why vertical stealth exists. To understand the F-35B, we have to understand who demanded it. The United States Marine Corps operates differently from the Air Force. They deploy from amphibious assault ships, smaller than full aircraft carriers. A Nimitz-class aircraft carrier is 333 meters long. And Wasp-class amphibious assault ship is about 257 meters, and not designed for catapults. No steam catapult. No electromagnetic launch system. No arresting gear capable of heavy recovery loads. So marine aircraft must either take off very short distances or land vertically. Historically, that meant the Harrier jump jet. But the Harrier had limitations. Subsonic, limited payload, no stealth, enormous maintenance demands. By the 1990s, radar-guided air defenses had improved dramatically. Stealth wasn't optional anymore. So the Marines wanted something unprecedented. A stealth aircraft, with internal weapons, capable of Mach 1.6, and vertical landing. This isn't an incremental upgrade. It's a violation of aerodynamic common sense. Part 2. The physics constraint. Hovering breaks fighters. Let's reduce the problem to first principles. In normal flight, lift equals 1/2 rho v superscript 2 sc. Lift depends on forward velocity. Without velocity, lift drops to 0. During hover, the wings are irrelevant. All lift must come from downward jet thrust. That means the engine must produce thrust equal to the full aircraft weight. The F-35B's maximum takeoff weight approaches 27,000 kilograms. That's 265,000 newtons of force required just to stay in the air. But here's the problem. A conventional fighter engine produces thrust backward, not downward. If you try to redirect all exhaust downward using rotating nozzles like the Harrier, you run into 3 catastrophic issues. Exhaust temperature exceeds 1,500 degrees Celsius. Ingested hot gas reduces engine efficiency. Thrust vectoring destabilizes control. Hot exhaust reflects off the ground. It rises. It gets sucked back into the intake. This is called hot gas ingestion. When that happens, engine thrust collapses. The aircraft falls. This is why hovering jets are unstable. Now add stealth constraints. Stealth requires a smooth, aligned surfaces, internal weapon bays, and no large openings or protrusions. A lift fan opening in the middle of the fuselage? That's a radar reflector nightmare. So engineers faced three competing laws: thermodynamics, aerodynamics, electromagnetics, and all three disagreed. And this is exactly why engineering like this is so fascinating. If you're enjoying this breakdown so far, make sure you're subscribed because the next project is even more insane. Part 3. The solution. The lift fan. The breakthrough didn't come from brute force. It came from separation. Instead of redirecting all engine exhaust downward, usins of RPM, cold air is pulled from above. It is forced downward through a variable nozzle. Cold air, not exhaust. This is critical because cold air reduces deck heating, prevents hot gas ingestion, improves thrust efficiency. Meanwhile, the rear exhaust rotates 90 degrees downward via a 3-bearing swivel module. The result? 2 vertical thrust columns. One in front, one in back. This creates balance. Instead of one unstable pivot point, you now have a stable thrust couple. In simple physics terms, torque is minimized. That's the hero moment. Part 4. The materials science nightmare. Now let's zoom deeper. The shaft connecting engine to lift fan transmits roughly 29,000 horsepower. That's more power than a Formula 1 grid combined. At extreme RPM. Inside a compact fuselage, the torque loads are enormous. Visual, stress simulation of drive shaft under torsion. Why doesn't the shaft twist apart? Materials science. High-strength nickel-based superalloys are used in the hot sections. Titanium alloys dominate structural regions. At the atomic level, these materials resist creep, permanent deformation under stress at high temperatures. Creep is deadly in turbine components. If turbine blades elongate even millimeters, they strike the casing. Engine failure. To prevent that, turbine blades are often single crystal castings, eliminating grain boundaries where creep begins. That's engineering at the crystallographic level. But there's a trade-off. These materials are expensive. Very expensive. Part 5. Stealth versus open holes. Here's the paradox. Stealth works by minimizing radar cross-section. The F-35's shaping reflects radar waves away from emitters. Visual. Radar wave deflection diagram. But the lift fan requires the top intake door, the bottom exhaust door. When open, these are massive cavities. Cavities are terrible for radar signature. So the solution: the doors only open during vertical operations. In cruise flight, the aircraft maintains low observable geometry. This is compromise engineering. It is not perfectly stealthy in hover, but it doesn't need to be, because hover operations happen near friendly ships, not enemy radar networks. Part 6. Control. The software layer. Hovering a 27-ton stealth jet manually would be nearly impossible. So much of the F-35B's success is software. The flight control system constantly adjusts roll posts in the wings, rear nozzle vector angle, lift fan pitch, hundreds of micro-adjustments per second. This is fly-by-wire taken to its extreme. The pilot doesn't control thrust directly. They request motion. The computer solves the physics. This is control theory in real time. Without modern processors, this aircraft would not exist. Part 7. The trade-offs. Now the uncomfortable part. The F-35B carries less internal fuel than the conventional F-35A. Range is reduced. Payload is reduced in vertical mode. Maintenance complexity is significantly higher. And cost? Unit cost has fluctuated around $100 million per aircraft depending on lot and accounting method. Operating cost per flight hour is high compared to legacy fighters. The lift fan system adds weight, dead weight, during conventional flight. It is in used mass for most missions. That's the compromise. The aircraft is optimized for flexibility, not pure performance. Part 8. The economic reality. Why build it at all? Because it allows small ships to deploy fifth-generation fighters. That changes force projection. A fleet of amphibious assault ships can operate stealth aircraft without needing full carriers. This disperses capability. From a strategic standpoint, that matters. From a physics standpoint, it's expensive. From an engineering standpoint, it's astonishing. The verdict: is the F-35B the best dogfighter ever built? No. Is it the most efficient aircraft ever made? Also no. But is it the only operational aircraft that can hover, fly supersonic, remain stealthy, and carry modern weapons internally? Yes. The F-35B is not perfect. It is a compromise machine. A machine built at the intersection of thermodynamics, aerodynamics, electromagnetics, materials science, and software control. It exists because engineers refused to accept that thrust-to-weight was the end of the story. They split the problem. They rerouted energy. They engineered around physics without breaking it. And that may be the most impressive thing of all. Because nature always wins, unless you understand it deeply enough to work with it. And the F-35B is what happens when you do.